Hi everyone, my name is Zhenminyu, a student from Dalhousie University. This video, I will introduce our work, Latent Concept-Based Explanation of NLP Models. I will start by discussing the motivation behind our work. As we all know, large language models are always black box. It poses the challenges for us to understand how this model works. For example, if we have the sentiment classification task, we will input our sentence into the large language models, and the model will output the final prediction. But we also want to know why the sentence is classified to this label. In these examples, we actually want to know why the model predicts this sentence as the negative sentiment. And a lot of current work use attribution-based methods to explain the model prediction based on how each input token contributes to the outcomes. In other words, the model calculates how much each word in a sentence influences a prediction. This helps us identify which words have the most impact on the model's decision-making process. In this example, the method calculates the attribution score for each input tokens, and we can find that the weaponized word has a high score, indicating it's the most important word driving the negative prediction. So the word weaponized is the explanation for the model prediction in the attribution method. However, this kind of explanation based solely on individual input words tend to be less informative due to the discrete nature of words. A word normally consists of multi-facets aspects. For instance, consider the word Trump. It can serve as a verb or a name entity representing certain aspects, such as US president's name, type name of cars, tower name, or family names. Thus, only using the words as an explanation cannot provide enough information for us to understand which aspect of the words the model used in the prediction. So to address these limitations, we propose our methods, Latent Concept Attribution method. We can also call it LACOAT method. This method aims to provide latent concept-based explanation for each input instance. So our idea is that given various counters of a word within the training data, the model learns these diverse facts during training time. In this example, assume Trump appears many times with different meaning in the training data sentence. The model should learn this diverse aspect of the word Trump in the training process. At inference time, the model will use a particular facet of the input words in making the prediction. So for the examples, assume the sentence here is the input instant at inference time. The model will use one facet of Trump in making the prediction, which is the US president's aspect of Trump in this example. And these diverse aspects learned by model in training time are the latent concepts. And we actually want to discover the latent concept from the training data and use them as the explanation for the model prediction in the inference time. So we want to use latent concept-based explanation instead of using only single words for explaining the model prediction. To better understand how the LACOAT method works, we will discuss the overview of our methods. In the training time, in the LACOAT methods, we will first to input the training set into a trained model. From there, we can extract the contextual embedding of the training data token from any layer, and let's assume we gather them from layer L here. Next, we will apply agglomerative hierarchy clustering to grouping the embeddings into clusters. Each cluster represents the latent concept within the training data. So here, this is different like the red one and the blue one are the different clusters. They are the different latent concept. And the point here is the word of that clusters. Finally, we train a concept mapper that takes these contextual embeddings as input. So the contextual embedding of each token as input, and use their corresponding class ID as labels. After training, we move on to inference time. First, we input a test instance into the trained model. Then the method extracts the contextual embedding of test instance from a layer, the same we use layer L, and identifies the most salient words using an attribution method. Next, the contextual embedding of salient words is passed into the concept mapper. Finally, the concept mapper links this embedding into a latent concept from the training data space. This mapped latent concept is the explanation for this input test instance. Next, we will see the example generated by LACOAT method. This is an example of a correct prediction. The sentence part refers to the input sentence. The prediction part is the model's output, and the true label is the gold standard label. And we actually have two explanations. The left side, we have the explanation based on latent concept. On the right side, there is a plausible explanation generated by a generative model, showing how the input sentence related to the latent concept content. And normally, latent concepts are presented in a word cloud format, but here we have the sentence format. So why is the concept content presented in sentence format rather than as word cloud here? And here is the reason. Because it is a sentiment classification task. The most important token at the final layer is the COS token. This leads to latent concept being formed from COS tokens of sentence that are most relevant to the input. If we were to represent these latent concepts as a word cloud, it won't be meaningful, as we'd only see the COS tokens in it. And here's how the explanation approach works. Each COS token is saved with a unique identifier, it's the sentence ID. So we will put sentence ID after COS, each COS token. And for interpretation, we randomly select 5 COS tokens from the latent concepts and use their corresponding sentence for these tokens as are displayed as the latent concept content. And back to the previous correct prediction examples, the latent concept-based explanations shows that most sentences are related to positive sentiment. And also from the plausible explanations, it highlights additional information about relations between the latent concepts and the input sentence. It reveals that the positive sentiment of them is driven by pricing different aspects of a film or about actors and actresses. For evaluation, we conducted many experiments to evaluate the performance of the explanations. First, we have qualitative and human evaluations that helps assess how effectiveness of the explanations are. Next, we have the module-specific explanation, which measures the performance of each individual part of the method. And finally, we have the faithfulness evaluation. It ensures that the latent concepts explanation are truly faithful to what the models has learned, and also validates the reliability of concepts themselves. Overall, the LACOAT method offers both a faithful and plausible explanations of a model prediction, and it demonstrates that the reliance on training data latent space enables interpreting how knowledge is structured in the network. And our work also evaluates the effectiveness, faithfulness, and plausibility of methods explanation. Thank you all for your attention. For more details, feel free to explore our paper.